Hi, my name is Martin, and we will now come to the hard stuff about web performance. The title in the Meetup said something about all browsers, but to be honest, I'm just focusing on Chrome. Stefan brought up the idea about this Meetup, and I thought to myself, yeah, cool, let's do that. I did a deep dive into the V8 1 year ago, 1.5 years ago, and thought, yeah, let's go in and see if it all is still the same. And I thought to myself, damn it, they changed it. They changed it drastically. So I have 2 points here: V8 before last month, this month, and the V8, how it will parse your and do your JavaScript up to version 59 or something like that. After that, there's also 2 important things to understand if you're going to if you want to make your JavaScript faster. It's the parsing, the initial parsing, and garbage collection. Yeah, let's dive into it. The compiler. The compiler, short history, the compiler looked in 2008. That was when Chrome was the fastest JavaScript engine. V8 was the fastest JavaScript engine on the market. It looked really simple. You have a JavaScript code, you put it in your parser, it creates an abstract syntax tree. So does everybody know what an AST is? Don't be shy, I didn't know it either. Okay, everybody knows it. I'm the stupid one. And the abstract syntax tree will go into a module called CodeGen, and it created semi-optimized code. It creates real machine code. That was 2008. 2010, they thought about how can we optimize the machine code, the code we generate from our JavaScript code. So they created Crankshaft. It's an optimizer. Crankshaft used the AST, and whenever code was hit often enough, it got hot, and the full code gen gave it to Crankshaft. It optimized it. Crankshaft optimized the code into really, really fast machine code, and whenever it hit a problem, it de-optimized it. It's totally normal to de-optimize your code in a not type-safe language like JavaScript. This was the time when you did the right things. You could write JavaScript code that was faster than Java. But they had to do TurboVan. TurboVan is more or less the same as Crankshaft, only for ASM.js code. So if you wrote JavaScript code in 2014 that was ASM compatible, the parser went to the abstract syntax tree, went to the full code gen. The full code gen did unoptimized machine code, and after a while, after some iterations, your JavaScript code went to the TurboVan because you wrote ASM code and was optimized to optimize machine code. Yeah, it got more complicated. Android, the Chrome Android development said, well, we need something else. They created an interpreter, the Ignition. The Ignition passed code to the full code gen. It created unoptimized machine code. The Ignition also created bytecode. That's not machine code, that's a more higher abstraction of the JavaScript code, but not machine code. And whenever something hit the hot zone, whenever something was hit often, it was passed to the Crankshaft, TurboVan, whatever, and got up to optimized machine code. And whenever the optimized machine code hit a problem, it de-optimized it back. Everybody had to look at the abstract syntax tree. This was really big. year 6 features weren't developed here, they were only developed here. So every year 6 code you wrote in Chrome in 2016 was just in Ignition. So it just came to TurboVan, it didn't came to Crankshaft. And Crankshaft said, oh, a try-catch block. It's not my problem, I go away. So at the beginning of this year, this would be the part where would explain what you can do to write code that is perfect for Crankshaft or for TurboVan. But we enable the future. The future looks like this. We kick out Crankshaft, we kick out the semi-optimized, pre-optimized machine code. We just need Ignition. We just create bytecode. The only one who's ever looking at the abstract syntax tree is Ignition. It creates bytecode. When the bytecode hits a hot state, it gets to the fast pass. So it will be passed to TurboVan. It gets to real machine code. This is the part where it's really fast. This is, you can look at it like the JVM bytecode. Anyone ever worked with Java? No Java? Java? Yeah, some? Okay. That's Ignition and that's TurboVan. Why did they do that? First, they wanted to create predictable optimization. With Crankshaft and TurboVan, the architecture you saw a few slides ago, it wasn't really predictable. Whenever the code saw a try-catch block or a for-in or something like that, there's a long list of things. It de-optimized the code. It went really, really slow. That was also a big problem. Was the non-optimized machine code was really, really, really large, and the bytecode is a big portion smaller. They did it because of mobile Chrome. Mobile Chrome just used bytecode in the beginning, and the bytecode is definitely more smaller than the semi-optimized machine code. What happens? Sorry. What happens is what also was a big decision maker is everything they created, the parser, TurboVan, everything is written so Ignition creates bytecode. They can use that to develop faster new features. ES7 is around the corner. Is 2016, I should say. And with that, they have less problems to create new features because they have less possibilities to create bugs. Yeah, how do you enable it? You have two options. You wait for Chrome 59. I'm currently running Chrome 48, so wait a month or so. Or you go to your flags and enable the V8 feature. Future. What changed and what didn't change? With Crankshaft, you had a lot of stuff you shouldn't do. You shouldn't use try-catch blocks. You shouldn't look at your arguments in a certain way. You shouldn't use ES6 features if you want it to be fast. You shouldn't use prototype bind, and the list is really, really long. Forget about this list. There are a lot of GitHub pages that show you lists of things you shouldn't do and how to avoid them and how to do them in another way so it gets fast. If you're one of the lucky guys and can always support only the newest Chrome, ignore those pages. If you're not so lucky, ignore those pages too, because you will get there soon. And when you get there, your code will be incredibly slow because you optimized premature. What's still doable? Write monomorphic code. Monomorphic code monomorphic is about the shape of your JavaScript objects. Whenever you create a JavaScript object or a function, your browser creates a shape. A shape means all properties, the names of the properties, all functions, the names of the functions. Is it strict mode or is it sloppy mode? And whenever you change the shape, for example, by deleting something from an object, from a JSON object, or by adding it afterwards, TurboWan sees, whoa, new shape, can't optimize it, go back to bytecode. So if you don't have to do it, don't add new properties to objects, don't remove properties from object. If you really have to remove, for example, foo.bar, just set it to null. It's better than delete foo.bar. Write type safe code. I know if you talk to JavaScript developers, they will hate you for that. But a function that can return a Boolean or an object depending on what happens, depending on what parameters you give them, will probably not be optimizable, because the machine code is, or the TurboWan creates machine code that needs type feedback. Write declarative code. What does that mean? Everybody did something like if object then, and then object dot foo, something like that. That's good, but that's really such a long list of bytecode you create. If you just want to be safe that your object is not undefined, check for it. Let's say if object unequals undefined or unequals null, it's faster and will get faster with TurboWan than just writing if object. Use maps. Who has not heard about maps? ES6 feature, awesome ES6 feature. Awesome, use it. Use sets, use weak maps, use all of it. In former times, a lot of people, me included, wrote maps like JSON objects where we added the key as a property and the value as the value of the key. Don't do that. I will come to it later why that is really bad. Don't use objects as maps. Don't change the schema of objects by adding or deleting properties. Don't change type of variables and function returns. Your TurboWan really hates it. Don't mix strict and sloppy mode. Sloppy mode is when you don't have strict mode enabled. Please don't use evil. It's not even, it's slow and it's evil. Don't use it, please. Let's come to the second part of my talk, the parser. The parser is the thing that creates from JavaScript code an abstract syntax tree. And why is it important to look at the parser? Because the parser does the first step before anything can happen. And it's really important if you want to optimize your startup time. V8 parsing looks like this. You have two modes in parsing, the eager mode and the lazy mode. The eager mode is a real parser. It creates the scene abstract syntax tree. It builds the scope of your application and it's done. The lazy parsing is more a pre-parsing. It skips functions. It doesn't build an abstract syntax tree. It builds a scope, and it's quite fast. It's especially on your startup time. It's important because it's 2 times faster than the parser. But if you're forced to parse it later, it's 1.5 times slower than the parser. So if you're somewhere in your application, you loaded your page and you hit lazy parsed code and it has to be parsed. It's okay, you're in your code, we're in the perception, it's okay, but on your startup time, it needs to be fast. You have to think about, should it be eager or lazy? I will show you the rules, what is eager or lazy. We are on the root scope of our JavaScript. So we are on, that's window.global, if you want to say so. If you create variables, they're eager. If you create functions like this, where it's a self-invoking function, it's eager. If you create a function like this, it's lazy. That means the parser will see function, some name, I don't care about the body, okay, the function ends, it's lazy, it's cool. If you want to make a function not self-invoked but parsed eager, just add an exclamation mark to the front. And if you use the comma separation functions, all functions will be parsed eager. If you bind your function to a variable, it's lazy. If you bind your function to a variable and invoke it here, it starts lazy, but it's get eager at the end. This is where you're really pissed your parser off. The parser thought, hey, cool, it's lazy, skip the body. Oh, damn, parents. Okay, let's go back, let's do it again. Yeah, don't do that. If you want to do that, use the self-invoking functions with the parents at the top. Why should we do the parsing thing? Why should we look at it? 10 to 15% of our loading time, of the time needed to run your JavaScript at the startup, is reserved for parsing. That's a lot. You can improve a really big, there's a big thing to improve. Also, parsing is quite slow. It takes 1 second to parse a 1 megabyte JavaScript file in Chrome. That's a hard fact, more or less. So if you want to, don't give the browser all your JavaScript at once, because whenever he sees JavaScript, he will parse it. That means less code at the beginning helps you to get faster startup time, because even if you don't need the code, even if you don't need the JavaScript code you send to the browser will parse it and will spend time on it. So the conclusion here is ship less code, use parents to force eager, where you need parsing, and just a hint, try optimize.js. It's a cool tool to that will look at your code, at your JavaScript code, and will give you hints where to use the parents tricks, the self-invoking trick, to make a lazy loaded function eager so it gets faster past. The results are roughly 15 to 20%. It's really, really important, really cool thing. Last but not least, garbage collection. If you have a Chrome MacBook like me, I have 32 gigabyte RAM. I'm really cool with that. But if you have a low-end smartphone, you probably have 500 megabyte to 1 gigabyte, and your memory is really valuable. So the browser tries to find everything, every object you created, every string variable you created, and decides if it needs it or if it can remove it to free space. There's a two-generation strategy here, the new space and the old space. The new space is where almost all objects are created. It's really fast in allocation, so the browser can really fast see, okay, I put it there. And it's really fast at garbage collection. and it only has between 1 megabyte and 8 megabytes, depending on your machine. When does the garbage collection in new space happens? Almost always. If you look at your page and look at the how do you call it, the DevTools, you can look at what time is used for garbage collection. You see it happens every second so often. The problem is, for garbage collection, the browser has to stop the execution of the JavaScript code. So if the garbage collection takes longer, you feel a stuttering animation, slow down, everything on your site doesn't respond. So it's really important to get fast garbage collection. If the garbage collection algorithm skips over an object, in Chrome it's 2 or 3 times, the object will move to the old space. Objects that survived garbage collections come to the old space. It's a slow garbage collection, so every time a garbage collection happens here, that's roughly every second, every 5 seconds, depending on your machine. The garbage collection is a really slow algorithm because it has to do a lot of digging into your code. The old space is divided into 5 heaps, and the last part of the talk will be about those 5 heaps. New space, old pointer space, we go through them one by one. The old pointer space, every object that has a pointer inside it, so an object that refers to an object that looks like it's a nested object, comes to this place. It's important to realize that for every pointer, Chrome has to look into every code in the new space, in the all old spaces, if there's a pointer. So those objects are really pain to garbage collect. A little bit better are old data spaces. It's the old data space, raw data objects, strings, numbers. If there's no pointer to this object, to one of those objects, the garbage collection can go over them and kill them. Large object space, everything that is too big. We're talking about 500 KB and up. Objects here will never be moved because it's too expensive. So if you create a lot of big objects, they all end up here and they won't be garbage collected. So try to create small objects. Also, the garbage collection creates an own memory space, so it's really memory intensive, those objects. Everything that has code inside it, it's just a special heap. Doesn't differ from the pointer space and the awesome map space, cell space, property space. I said before, use maps and not objects, because objects as maps get into the large object space. We don't want anything to be there. We want everything to be in this map space. This heap is reserved for everything that is with maps, with sets, with weak maps. Everything will end up here. Yeah, conclusion. Big objects get own space. You shouldn't do that. Use maps. And the best garbage collection is in the new space. So we want your young objects to die young. This is really important. Don't hold up objects longer than they are needed. Yeah, that's it from me. That's my cat. Any questions? First, second.
So you mentioned that one of the things, the important things we should do is actually writing typeset code.
Yes.
So do you know what's the performance penalty, if any, of using TypeScript and more?
if you write, well, the TypeScript compiler is all slow. It's really almost nothing of the TypeScript compiler gets to the fast zone in Node.js. So compiling on the browser, compiling TypeScript on the browser, I wouldn't recommend it. The code that is produced by TypeScript is fast because it's type safe. It's not type safe for the eye. If you look at the code TypeScript creates, it doesn't look type safe, but the compiler recognizes, oh, there's always a string in there. Oh, there's always a number in there. Okay, let's put it to the fast path. So using TypeScript, yes. Compiling TypeScript on your machine in the build time, yes. Compiling TypeScript on your browser, don't do it.
Yeah. So you said that the big object should be avoided, but does the size of object include the object property values?
Sorry, again.
So does the size of object include the size of the object's property values, or is it only about the number of keys?
So if you have if your properties are primitive, they are part of the object. If your properties are objects, nested objects, you can get pointers. If you use something like let A be a big object and let B be a small object with a pointer to A, A will be in a large heap and B will be in a pointer space. So only one of those gets a penalty. If you write it in one will get a big. It's not about. It's really about the real size of your JSON, or about the JSON you write. That's depending on if you get into the big heap.
You're speaking about Chrome, but I was wondering if these kind of optimization strategies would work in other browsers as well, or if there's any major differences.
Parsing is part of each browser. I'll look it up. IE doesn't do it. Edge does it. Firefox did it. Chrome thinks about maybe removing it, or making it unneeded. So it depends. The do's do's and don'ts I wrote here are safe for all browsers. Every browser engine that wants to optimize your JavaScript code has the same problems. Monomorphic code, for example, it's about the shape. Chrome allows you if Chrome sees an object and it changes the shape 2 times, so you have 3 shapes, it says, okay, I can optimize that. Edge, for example, kicks you out of the fast code even if you change it once. So those do's and don'ts are for all browsers. Garbage collection, more or less the same. All browsers have tried to optimize the garbage collection because it's really expensive. And for all browsers, it's the best thing to have young objects or variables dying young. The heaps are differing on each of those. Yeah.
Just want to mention that Firefox recently announced their project Quantum, which is their new compiler, their new browser engine. And I believe, I'm pretty sure actually these things that he mentioned about the importance we should do, considering type-safe code, for sure it's fine for project Quantum as well, and write declarative code too. I'm not sure for the rest, but for those two, for sure.
I'm sure for the old Firefox that the monomorphic still counts. I'm not sure for the maps. I'm not sure how Firefox and Edge implemented maps, if they use a special heap for that and a garbage collection. But in general, I think they will do, for special abstract data structures, they will do special treatment to, yeah. No questions. Thank you.